Hello everyone, and now I want to discuss the linkage between the periodic table and electron configuration you learned from the previous unit based on Schrödinger's quantum mechanical model. So as you can see here, this is the modern periodic table organized by grouping elements with similar chemical properties and physical properties into groups called the columns in the groups or families, and then organize them with the ever-increasing atomic number, essentially number of protons in the nucleus. And there are about 18 groups, 7 periods, and 2 series, and it's organized in a very neat way. And as you remember, at the origin, the very beginning of the periodic table, Mendeleev is credited with the setup of the first modern periodic table. At that time, it's 20 years prior to the discovery of first subatomic particles. So he had no clue about the electrons, even the electron configurations. So now you already understand the setup, the major features of the periodic table. We're going to looking at how the electron configuration based on Schrödinger's model, quantum mechanical model, fits into this whole picture. And let's do a little bit of review on the Schrödinger's model. Quantum mechanical model of atoms. So at the very in the middle, you're going to have a nucleus, and surrounding that you're going to have got to draw it better. So surrounding it you're going to have these circles. Remember what we call those circles? 3, 4, 5. I really need to practice my drawing skills. What do we have on those? Those circles are called principal energy levels, and I will just use the color. This one, it will be n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, and the list goes on and on. This is quite similar to the Bohr's model I just mentioned before, but on those principal energy levels, now you have sublevels. This one will have 1s, and another 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, and 5 have 5s, 5p, 5d, 5f, actually 5g. Remember, for ground state electron configuration, for all the elements, we'll probably never will never get to 5g, but it's still there. Now on those sublevels we have orbitals. We have orbitals with each little box, and 2s has 1 box, 3 has 1 box, 4 has 1 box, 5s has 1 box. Remember the number of boxes associated with each sublevels, the S, P, D, F, G, H, I, and the list goes on, has a lot to do with the interplay between the N, the L, and the M. The N, L, and M. So 2p should have 3 boxes, 3p should have 3 boxes, 4p also have 3 boxes, 5p 3 boxes, 3d should have 5 boxes, 1, 2, 3, 4, 3D should have 5 boxes. 1, 2, 3, 4. 5D, 1, 2, 3, 4. 3F should have 7. 1, 2, 3, 4, 5, 6. And 2, 3, 4, 5, 6. And this one, 5G should have 9. 1, 2, 3, 4, 5, 6, 7, 8. And as indicated by the Pauli exclusion principle, each box maximally holds 2 electrons, and they have to spin in the opposite direction. Also, for the Aufbau principle, we have to arrange them. From the bottom up. And remember, the sequence where we want to do it is n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, n equals 6, n equals 7. So this one will have 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 5g, and the list goes on. Now you start to get the hang of this. We're going to draw diagonal lines to get the sequence. This will be the sequence of filling in these sublevels, and the list goes on now. So this one coupled with the Hunt rule, and we can have a complete picture of how electrons are organized surrounding nucleus of each element at its lowest possible energy state. We call it the ground state. So then let's go back, take a look at the group 1 elements. Group 1 elements including hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. This column. Let's take a look at the electron configurations. Okay, so I just want to put it into a particular format. So we're looking at group 1 elements. What we want to have is the ground state electron configuration. Okay, lowest possible energy state, and we want to say like that. Based on that, we're going to do the circular plot, and based on circular plot, we do want to do the valence shell electron configuration. And the last, we want to look at the Lewis dot structure. Okay, so Lewis dot structure. The first one we're looking at is hydrogen. Let's change in color. Let's change in a color. I like to use the red one. If we're looking at hydrogen, ground state electron configuration was 1s1. Circular plot, we have a +1 in here. It's one circle with 1 electron on it. And the valence shell electron configuration, 1s1, and the hydrogen has a single dot. The next one will be lithium. Next one will be lithium. That will be lithium number 3, 1s2, 2s1 now. So we have a +3, 2 circles, and there's 2 electrons and there's 1 electrons. Then this is gonna switch back to the color. So erase this first and switch back to the color. So it will be 2s1, and Lewis dot structure, lithium, a single dot. You see something interesting. Continue. The next one on the one will be 1 row lower on period 3, and now you have sodium. Now sodium has 11 electrons. 1s2, 2s2, 2p6, 3s1. So you have a plus 11 in the middle, and that's not a very good drawing. So then let's we have 3 now. Now we have 3, and we have all those electrons moving, arranging it. 2 on the first ring, 8 now on the 5, 6, 7, 8. 8 on the second ring, and on the third ring we'll have 1. And now we have, what we have is 3s1 and sodium as a single dot. Let's take a look at let's take a look at the last one, not the last one, this next one of this element on this, in this group. That will be potassium. Potassium has got 19, so it's 1s2, 2s2, 2p6, and 3s2, 3p6, 4s1. So now I have a plus 19, 4 rings, because I have a 4s1. 1, 2, 3, 4. Then you can have the 2 on the first ring, 8, 8, second ring, 8, on the third ring, and 1 on the last ring. And this one will be have a 4s1. Potassium will be 1 dot. Now you start looking at very interesting pattern. Okay, so now you probably can start predict the next one. Cesium will be 5s1, and cesium lowest dot structure will be cesium plus a single dot. Let's see some of the other groups, whether we have a similar trend or not. To save time, I actually constructed those ground state electron configuration circular plot, valence shell electron configuration lowest dot structure for the other groups prior to the start of this podcast. So here we are looking at the group 2, beryllium, magnesium, calcium. Write down all the ground state electron configuration, and there should be a routine now for you. It's based on the previous unit. And now we have the circular plot: 2 circles for beryllium, 3 circles for magnesium, and 4 circles for calcium. And this still is slightly different from the first one, but they do kind of quite similar: 2s2, 3s2, 4s2. Now you have, then you can translate them into the orbital notation. This is a paired on the 3s sublevel, so you have a paired electrons as the lowest dot structure. As we can go down, we probably can predict what's the next. That will be the barium for this group, or will be the lowest dot structure. Will be barium with a pair of dot, and valence shell electron configuration will be the 5s2. Now I start looking at this. Also another correlation is beryllium is on period 2, it ended up with 2s2. Magnesium is on period 3, you end up with 3s2. Calcium is on period 4, you end up with 4s2. It's 4 rings, 3 rings, 2 rings. I want you to keep that in mind. And let's switch gear, bypass all the transition metals. We probably will come back and revisit this at a later time. And now going on to the group 13, you have boron, aluminum, and gallium. So all the ground state electron configuration, you can write it down here. Circular plot, you can construct it accordingly. Now gallium, you can start seeing the third one has 18 electrons. Why? Now you have a 3d10. However, the valence electron configuration is 2s2 2p1 for boron, and 3s2 3p1 for aluminum, 4s2 4p1 for gallium. And also, according to, translate those ground state electron configuration to valence shell, to do the orbital notation, you will see it's a pair and a dot, it's a pair and a dot, it's a pair and a dot. Similar pattern. It keeps on going. So for the last group I want to demonstrate, showing that it will be the last one, the group 18 noble gases, and the elements helium, neon, argon. And helium has only 2 electrons. So for the circle, to complete that, it should have only 2 dots, and 2 dots for here. For neon, got a 10, so it's 8 for the outside. Argon, 2 here, 8 here, 8 on the outside. Okay, and the valence shell electron configuration is 1s2, 2s2 2p6, 3s2 3p6, and for Lewis dot structure, helium is dot, neon 4 pairs of dots, and argon is 4 pairs of dots. So in terms of trends, the helium stands out as compared to the others. All the others now have 8 valence electrons, 4 pairs. So for the noble gases, they all have 8 valence electrons, except the exception will be for helium. The reason for that is helium has only 1 ring. As you have only 1 ring, the most number of electrons you can accommodate, 2, because you only have 1 s sublevel. There's only 1 orbital on that, and Pauli exclusion principle dictates your maximum. You have 2 electrons. So now you are clearly start seeing the pattern now. So what you can conclude actually is, if we're looking at the periodic table, for the elements in the same families or groups, the same column, they all share the same valence electron configuration and the same Lewis dot structure. The number of rings corresponding to the valence shell, the n, is exactly matching the number for the periods. So then if we can come up with some generalized representation and for those groups, and you can see for group 1, valence shell electron configuration will be the ns1. N stands for the period number where the elements are located, where the element is located. Lewis dot structure will be X, using X as the symbol for the elements in that particular group. We should only have 1 dot. For group 2, you'll have NS2 now, and X should have a pair. For 13, and now you have NS2, and P1 should have a pair of dots plus a single. 14 NS2, and P2, you should have X, a pair, and 2 singles. Remember that, very importantly, it's 2 singles instead of a pair, dictated by what? The Hund's rule. P orbitals, 3 orbitals, same energy, so we have to fill them 1 each electron, same spin direction, before we can come back and pair them up. 15 NS2, and P3, and that would be 1 pair, 3 singles. 16 NS2, and P4, and that would be 2 pairs and 2 singles. 17 NS2, and P4, and 3 pairs and a single. And 18 NS2, and P6, X will have 4 pairs. So this asteroid, the exception will be helium. Helium only have 2, and that is a pair. So now you can see this is so well organized. And the other interesting feature I'd like to point it out is, as you can see, the group 1 and 2, the highest, the sublevel with the highest energy, which means it's filled the latest sublevel. This is ended up on S, so it's an S1 and S2. Now we start looking at on the 13 will be the highest energy sublevel will be the P, NS2 NP1, NS2 NP2, all the way to NS2 NP6. And now it's very interesting. If you write the electron configuration for this, you are looking at the d orbitals starts to get filled up. If you write electron configuration for this, you're going to say f orbitals starts to get filled up. And very interestingly, there are 2 columns for the ones end up with S, 6 columns for the one end up with P, 10 columns if you count correctly for the one end up with D, and 14 columns when the ones end up with F. And there's 2, 6, 10, and 14. This combination of numbers should sound familiar to you, because 2 maximum number of electrons can be accommodated on the S sublevel. 6 maximum number of electrons can be accommodated on the P sublevel. 10 that will be on the D sublevel, and 14 that will be on the F sublevel. So in terms of organization, again based on electron configuration, these 2 first columns is what we call S block elements. This 6 we call it P block elements. Transition metals we call it D block elements, and lanthanoids and actinoids, those 2 series, we call it F block elements. Now you start seeing this as extraordinarily matching between the periodic table, the initial arrangement of periodic table, and the electron configurations. So you should draw a conclusion, because the periodic table mainly was initially arranged based on similarity in chemical properties. So now especially the valence shell electron configuration will be the determining factor for the chemical properties. The reason why they all exhibit within the same group of families elements exhibit similar chemical properties is because they have the identical valence shell electron configurations. So with all those generalized formulas and the Lewis dot structures, we can use this periodic table, we can use this modern periodic table quickly write the electron configurations for all those elements, especially the valence shell electron configurations. And based on that, resolve lots of problems. To recapture, well, we went through the exercise, the examples. Now we realize that the organization of the periodic table initially was based on the chemical similarity and chemical properties. From the other perspective, based on Schrodinger's quantum mechanical model, it actually exactly matches the electron configurations, and especially for the valence shell electron configurations for each family or group elements, which within this family or group all have the exact same valence electron configuration, albeit they on the different shells. But the numbers of valence electrons are the same, Lewis dot structure are the same. And now you can say you have generic forms that represents the valence shell electron configuration Lewis star structure. With that, I conclude this podcast. Thank you very much for your attention. Don't forget to work on the questions, solve the problems on the worksheets to reinforce the learning you just had.